In this video, we're going to discuss what we call the second derivative. Since the derivative itself is a function, we can calculate its derivative, right? So since we already know that f prime is a function, then we can calculate its derivative. So for a function f, the derivative of its derivative is called the second derivative. I'm going to use the numerical second derivative. And if we have f of x, then we say it's f double prime of x, all right? And so just to get used to some notation, when we have y equals f of x, our first derivative is f prime, but remember we can also write that in Leibniz notation. And so since we said that y was a function of x, we wrote that as dy dx, okay? So for the second derivative, we got to be able to notate why this is the second derivative, and we usually write it like this, d2y, it looks like a d squared y, over dx squared. All right, and this notation looks weird, like why is that 2 on the d? Remember when I said that the derivative itself can be considered an operator? And so if I would write the first derivative as d dx of f of x. And so if I want to notate the second derivative, I'll say do the second derivative of f of x, or you can say y. You can put y there. Y is the same thing as f of x, but I want to keep it as f of x. And this sort of can explain why the d2y sub dx squared is the kind of notation that we have. It kind of comes from this thinking of the derivative as an operator. All right. What does the second derivative tell us about the first derivative? We want to be able to know the relationship between the second derivative, the first derivative, and the function. And we want to know all the interconnected relationships. Well, since the second derivative is the derivative of the first derivative, it's basically going to tell us the same thing that the first derivative told us about the function. We said that when our first derivative was greater than 0, then our function is increasing. When it was less than 0 or negative, then our function is decreasing. And when it's equal to 0, our function is neither increasing nor decreasing, right? And so this is what the derivative of f told us about f. That's always the relationship between a function and its derivative. And so we can translate that to be the relationship between the second derivative. Look at this now. This is the second derivative. This is what the second derivative tells us about the first derivative, which if I take the derivative of f prime, I get to f double prime, just as if I take the derivative of f and I get f prime, right? There we go. And so I basically can fill this chart in the same way, where the second derivative is greater than 0 or positive. That means the first derivative is increasing, okay? Where the second derivative is negative, that means the first derivative is decreasing. And then when the second derivative equals 0, that means the first derivative is neither increasing nor decreasing. And we saw that there's going to be a horizontal tangent line when that happens on our graph. All right. So that's the relationship. So this isn't new, right? So in all the graphs where we looked at the given graph of the function and we were trying to graph its derivative, that same relationship would happen if I gave you the graph of the first derivative and ask you to graph the second derivative, right? And then we looked at graphs where I give you the first derivative and you go and try to graph the function. Well, I can give you the second derivative and you do the exact same thing to be able to graph the first derivative function, right? Now let's get into what does the second derivative tell you about the function, all right? We know it tells that the second derivative tells us where the first derivative is increasing, decreasing, or neither increasing or decreasing. But what does that second derivative tell us about the entire function, the original function? And we're going to look at this here. We know that when our first derivative is increasing, our second derivative is greater than 0. When our first derivative is decreasing, our second derivative is less than 0, right? We already found that out in this table here. So I have two graphs here, all right? And one of these graphs looks like an upside down parabola. This one looks like a right side up parabola, right? And in these cases, I want to see if f prime of x is increasing or decreasing. Now, if you want to see if something is increasing or decreasing, you have to do it over an interval, right? You got to know, you can't just look at one spot. You got to know, do it over an interval. By the way, this is just regular old f of x graphed here. Regular old f of x graphed here too, all right? But we want to know if f prime is increasing. Is the derivative increasing? Well, when I'm looking at the regular function and I want to know if anything about the derivative, I've got to look at slopes of tangent lines, right? And so my derivative f prime, I'm going to pick a few points. All right, I'm going to draw some tangent lines at these points. So we have horizontal right there. If I want to know what's happening to my first derivative, right? All right, I'm going to do an f prime line. All right. This is a slope of a line, right? This line is going up. This tangent line at this point is going up from left to right. So my derivative at this point is positive, right? This one is also positive, right? But it is not as steep as this one, but it's still positive, right? Here, my tangent line is 0. So my derivative is 0 there. Here, my tangent line is going down from left to right, so the derivative or the slope will be negative. So my derivative will be negative. And in here, it's even more negative because it's steep. So it's becoming more negative, right? This is what my derivative is doing. My derivative is being a positive number, a less positive number, 0, a negative number, and then more negative. This is telling me that f prime of x is decreasing. Okay? We just found out that when f prime of x is decreasing from left to right, my slopes of my tangent lines are getting smaller and smaller, right? That means if I go back to this chart up here, when my function's derivative f prime is decreasing, the second derivative is negative. So that means f double prime of x is negative. All right. We're going to do the exact same thing on this picture to the right, right? I have f of x, and I want to know if f prime is increasing or decreasing. So I'm going to choose some points. 1 point, 2 point, and I'm randomly choosing points. You don't have to choose these exact points. I'm going to draw tangent lines because I want to know about the derivative. I'm not concerned about f right now. I'm looking at the derivative. Horizontal tangent line, positive slope, and even more positive slope. So what's happening here is that my derivative is starting out very negative. That's a very steep negative line. So it's negative. This one is still negative. It's going down from left to right, but it's not as steep. So it's a little less negative. Here I have a horizontal tangent line. So my derivative is 0. Slope of that line will be 0. It's horizontal. The slope becomes positive here, and it becomes a positive steep line, sloping line. So that's more positive, right? So my derivative is going from being a negative value, a less negative value, 0, a positive value, and then a more positive value, right? That means my first derivative is increasing. When the first derivative is increasing, f prime of x is increasing, the second derivative is positive. Now, I specifically chose this function here because I want to know what the second derivative tells us about the function itself, which we have graphed here, right? On this entire interval, f double prime of x is negative, and my function looks like this. My function is concave down. And so what the second derivative tells me is the concavity of my function. My second derivative tells me the concavity of my function is opening downward that entire interval where f prime is decreasing and f double prime is negative. When f prime is increasing and f double prime is positive, my function f of x is concave up. So let's summarize this relationship in this next box here. What does the second derivative tell you about the function? So I got the second derivative and the function. When f double prime is greater than 0, f of x is concave up, like we had in this example to the right. And when f double prime is less than 0 or negative, then that means your function f is concave down. And when f double prime equals 0, we didn't see that case there, but it's going to be f of x is neither concave up nor concave down. What that means is that it's either changing concavity or it's linear. For instance, a function that looks like this, a linear function, it doesn't have a curvature at all, so it doesn't have any concavity, right? So it's neither concave up nor concave down, all right? So that's what happens when f double prime equals 0. It's either changing concavity or it's linear, all right? So let's look at some examples here. In example 2, it says in the graph below, the second derivative at points A, B, and C, so those are x coordinates to our graph, is what? Well, when we talk about the second derivative, we got to look, and we're given the function, right? Because this says f of x. It doesn't say f double prime. It doesn't say f prime of x, right? It says f of x. So if I want to know the sign of the second derivative and I'm looking at the graph of the function, all I have to do is determine whether the graph is concave up, concave down, or neither, okay? So at this point A, which has this point here, my graph is concave down. At C, my graph is concave up, and it is at point B where it looks like it's neither. So when your graph is concave down, your second derivative is negative. When it's neither, your second derivative is 0. And when it's concave up, your second derivative is positive. And so I should look at negative, 0, positive. That would be answer choice B. In the graph below, at x equals 0, the signs of the function, the first derivative, and the second derivative in order are, all right, so when we talk about the function, right, f of x, this is the graph of f of x here, right? They give us the graph of f of x. We want to know the sign, that means positive, negative, or 0. When you're talking about the function, you're talking about the y value. So what is the functional value at 0, right? Is it positive, negative, or 0? Well, it goes through the order pair 0, 4. So the functional value is actually y equals 4, which is positive. So we know that the functional value is positive. The first derivative, right? Well, when we're given the function, when we talk about the first derivative, we're talking about the slope of the tangent line, right? So f prime of 0 has to do with the slope of the tangent line, and the slope of the tangent line at that point equals 0, right? So we get 0 for the first derivative sign. And then the sign of the second derivative has to do with concavity. So if we want to know the sign of f double prime of 0, we have to look at the concavity. And since it's going something like that, it's concave down. And when it's concave down, that means it's negative or less than 0, right? And so I get positive, 0, negative. The answer to that would be B. Positive, 0, negative. Which of the following graphs could represent the second derivative of the function to the right? I'm doing this example as a multiple choice so that you'll know how you should do your homework. Like if I go to my homework and it's a multiple choice question, I'm not even going to look at my answer choices before I try to figure this out. What I'm going to try to do is I'm going to try to use the graph on my paper, and I'm going to try to figure out what my answer is I'm going to try to draw the graph without looking at any of these graphs here, right? If this is f of x and we want to graph the second derivative, we have to look at where the function is concave up, concave down, and neither. For instance, all right, my graph is automatically going to have arrows here because there's no endpoint, right? my graph first starts out being concave up. And it's concave up until I get to somewhere in this area, right? So I'm going to put a CCU for concave up. After that concave up part, my graph starts to be concave down from here all the way until I get to about here, concave down. Then it switches concavity and becomes concave up again, which is here, concave up. So somewhere in this region between -1 and -2, my graph changes concavity, and also between 0 and 1, it changes concavity again, right? So that will probably be points where it's neither concave up nor concave down. Now, when my function is concave up, this is a second derivative line. My second derivative is positive. When it's concave down, my second derivative is negative. And when it's concave up, my second derivative is positive. So I need to see a function that goes positive, negative, positive when I graph my second derivative. So I'm going to try to plot those 2 points. All right, I don't know what they are, but this is close to -1, maybe -1.3, and this is maybe 0.5, right? My function should be positive. It equals 0 there. It should be negative, and then it should become positive. That would be a good sketch of this second derivative here, right? And so my answer choice A doesn't do that. My answer choice B doesn't do that. My answer choice D, it looks like it does it. C does not, and D look like it does, right? Because we're starting concave up, down, up, positive, negative, positive. That means my answer choice should be D, all right? And there we go, right? So if you're ever given some answer choices on your homework that are multiple choice, try to learn and do the actual problem without working from the answers, because as you know, your exams, you will not be working from answers. You will be you'll have to do this on your own. And so get in the practice of doing that, even if your homework seems to not require you to do so. All right. Let's look at one more example, right? We've gotten used to looking at these graphs here, right? Looking at the concavity and all of that stuff, knowing these concepts. Let's now look at this last example here. Sorry for all the scrolling, where we will look at the table of values. It says a balloon is blown up. Between each breath, which is given by X, the circumference C of the balloon in inches is measured, and it's recorded in the table. We have C, which is the circumference, as a function of X, which is the breath, right? You take one breath, 2 breaths, measure the circumference. The third breath, you measure the circumference, so on and so forth. Part A says, determine the sign of the first derivative using average rate of change. All right, now you can tell the sign of the first derivative without using average rate of change. I'm going to tell you that right now, right? The sign of the first derivative, when you're given the function, is to determine, if you're given the function, you need to see whether the function is increasing, decreasing, or neither increasing nor decreasing. As we look at these numbers in the table, we can tell that the function is increasing. The output values goes from 16.8 to 21.2 to 24.2, all the way up to 33.6. It goes up every time. So we know that the sign of the first derivative is positive, right? But you can also use your average rate of change, and you can use the average rate of change to give you an estimate for your derivative when you're given a table of values, right? So if I use my average rate of change, I could actually get an estimate. Now, this is an estimate. It may not be the best estimate, but it gives me an approximate estimate of C prime of X. Now, I'm going to do the right-sided average rate of change. So from 1 to 2, I'm going to do that average rate of change and let that be an estimate for C prime of 1. I'm going to use the average rate of change from 2 to 3 and let that be the estimate of the derivative at X equals 2, and so on and so forth. And actually, once I get to 8, so if I do the average rate of change from 7 to 8, notice I can't do a right-sided average rate of change for 8, and so I'm going to do the same thing. I'm going to do a left-handed derivative estimate for X equals 8, all right? But remember, your average rate of change, you take your C of 2 minus C of 1 all over 2 minus 1. That's 21.2 minus 16.8 over 1. And that equals, I've already done the calculations, 4.4. Then I do it from 2 to 3. So I do the 24.2 minus the 21.3 divided by 3 minus 2, which is 1. And we get 3, right? And notice these x values are always 1 unit apart. So that division in the denominator is always going to be 1. So it's basically the change from one from one y value to the next. So I'm going to go ahead and fill in the chart with all the rates of changes, average rates of changes, estimates. 1.6. And again, because I can't do 8 to 9, I'm using 8 and 7 twice, all right? But as you can see, the sign of our first derivative is just the sign of the values that I see. 4.4 is a positive number. 3 is a positive number. 2.5 is a positive number. 2 is a positive number. All of these numbers are positive, so the sign of the first derivative is positive because the average rate of change is positive on each interval. And I use the average rate of change as an estimate for the instantaneous rate of change, which is your first derivative, all right? In part B, it says determine the sign of the second derivative using average rate of change. And that's why I really did this chart here using average rate of change. Because if I know an estimate for the derivative at each of those points, the 4.4, the 3, the 2.5, and I want to know something about the second derivative, and I have the first derivative, all I have to do is look at whether the first derivative is increasing, decreasing, or not, or neither, in order to tell me whether my second derivative is positive, negative, or 0. So if I look at these values of average rate of change, it goes from 4.4, it goes to 3, it goes to 2.5, it goes to 2. In each of those intervals, it goes down, right? Of course, because we're using the same value here, it's not going down. It looks like it's remaining constant. However, for all of these values up front, our rate of change or our derivative is going down, decreasing. And when the first derivative is decreasing, the second derivative is negative. So f double prime of x is negative because the average rate of change is decreasing. And remember, your average rate of change is your estimate. That's the estimate of f prime. And so when f prime is decreasing, we know f double prime is negative. All right, that concludes the concepts for this section on the second derivative. I'll see you in the next video.